So one further thing to note is how you would get the inverse trig functions out of SymPy. And they are just sp dot a sine, that gets you arc sine, right? Inverse sine. And SymPy can even demonstrate to you what is the derivative of arc sine. So it is 1 over square root. Well, they say it in the reverse order, I think because they like descending degree when they state their polynomials. But in any case, this is essentially square root 1 minus x squared, which is exactly what I said. And you can even pretty print it to get it to look a little bit better. But in any case, that's how you get the inverse trig functions out of SymPy. Now, moving on to what I promised, we will talk about the derivative of the logarithm. Now, if you just want what is the derivative of the logarithm, it is 1 over x, and you can, stop watching the video if you don't care about the proof, but I'll start giving the proof. Now, I will admit that this proof is not conceptually difficult the way that earlier proofs have been, but it is kind of difficult algebraically just because it's kind of hard to motivate why did I make all of the choices of manipulations that I made. And so I admit that that will be hard, but I'll try at every step along the way to say something about why I thought to do what I thought to do. So we start with just the statement of the derivative, right? The bare expression of what the derivative is by the definition. And I use the logarithm, right? I mean, what else do you do but just whatever comes first to your mind? And of course, if we're taking a difference of logarithms, we should know from high school that you can combine them into a fraction like this. Now, the next thing that I start to think about is I would like, I know that I've got ln here, and I know that it is the inverse of e to the x, and I'm dealing with limits. And by the way, I guess I really should have put in here that the definition of e to the x is the limit. So bear with me as I write this on the screen. The limit as n goes to infinity of 1 plus 1 over n to the n. That's equal to e. And if I just put x in the exponent on both sides, then I have e to the x. But I'll just leave it at this. And so since I know that this is what e is, and this has ln in it, and man, it seems like with a little bit of manipulation, I could get that sort of 1 plus 1 over business kind of going on. So, but how do I do it? Well, for one thing, it would be nice to distribute this division, except that you can't because the thing that's in two pieces is on the bottom and you can't distribute that way. But here's what you can do, is you can raise everything to a -1 power and flip it upside down, and then you can distribute. So that seems like a good way to go, and working me towards what you see here in E. And just having the kind of faith that if we kind of move in this way, I'll have E inside of ln somehow, some way, and make some kind of use of that, knowing that ln and E combine in some kind of particularly simple way. So that's what I do. That's why I raise this to a -1 power and flip everything upside down. And also, hey, why not use that extra logarithm rule that says that if you multiply the logarithm by anything, you can just move it into the exponent. That is a high school logarithm law, and I regard dividing by h as the same thing as multiplying by 1 over h, so that's why I get to move 1 over h into the exponent. And again, it's negative because I'm flipping it upside down. Anyway, the next thing that I do is, now that I've reached this point, I am sort of saying, well, okay, I want this to basically be like n, right? I want it to be simple, not this minus x over h. I want it to just be some simple one variable quantity. Let's call it n, right? Maybe I'll even explicitly say I'm going to call that n. And if I'm going to call that n, I also need n to be up here. So up here in the exponent, I need to force x to get into the picture somehow. And so in order to get x into the picture, I multiply top and bottom by x. And in doing so, I've got negative x over h up here. And so that's n, right? N is now up there and n is down here, kind of by forcing it into the picture, although things worked out a little nicely. But in any case, there I justify moving on to the next phase of my plan here. But notice that also the limit has to be going to infinity. And indeed, since I'm defining n to be x over h, as h goes to 0, this quantity, for any fixed x, this is going to go to infinity. Well, except for 0, but we could worry about that later if we wanted to. In any case, I am justified in replacing the limit as h goes to 0 with the limit as n goes to infinity, because as h goes to 0, n goes to infinity. Okay, so at this point, this is looking very, very close to ln of e. Just I've got this little over x problem to work with, but that's very easy to deal with. I just use the fact that if anything's in the exponent, I can make it multiplication outside, just the reverse of the thing I used a minute ago. And so I just take 1 over x, I move it to the outside. This is now ln of e, which you should know is equal to 1. So this is 1 over x times 1. There you have it. There's the proof that the derivative of ln is 1 over x.